We already knew that mu1 and mu2 were 8 and 10. So mu1 is 8, mu2 is 10. So in order to check the system stability, because if the system is not stable, we don't continue forward, we basically say that L and W are infinite. So for the system stability, we have lambda 1 less than mu1 and lambda 2 less than mu2. These conditions are satisfied. Are these satisfied here? 6 is less than 8, 8 is less than 10, so this is correct. Since this is correct, we continue. Okay. So these are the stability conditions. Given that stability conditions are satisfied, we proceed with the formulas for L and W. L is lambda 1 over mu 1 minus lambda 1 plus lambda 2 over mu 2 minus lambda. You know the lambdas and mu's, so we can substitute them. This is 6 over 8 minus 6 plus 8 minus 8, which comes to 7. Next is W. W is L over total arrival rate, which is R1 plus R2, which is 9 in this case, which is 7. So L and W are solved just as an extra thing. Probability that there are n customers at server 1 and m at server 2 is the product of the two, which will be lambda over mu for the first one, the n 1 minus lambda by mu times for the second one lambda by mu 8 by 10 to the power m 1 minus 8, which is 1 by 20. Fourth n. Any questions on this example?
Why was WL divided by 9?
Great question. So this is the overall arrival rate, and we did the arrival rate is the total external arrival rate, and external arrival rate is the sum of r's. So in our problem, the sum of r's is 4 plus 5, which is 9.
Thank you.
Any other questions? Right. So the syllabus of test 3 is till now whatever has been covered. So if we look at the books, So in the Solberg book, this was 5.16 was person death process, 5.13 was um, steady state probabilities, then chapter 6, and then open network part of chapter 7. Then the other book was कोई करनी book. So limiting behavior in this book is 4.6, and queuing models is chapter 6. Yeah, chapter 6 includes the Jackson networks. This book does not have closed queue, so this only has open queues. Yes. So 6.6 here we did not cover. So 6.6 was we covered MG1 but not GM1. All right. So homework. Um, what is the number of the homework? The last one. Right. Whichever it is, it's due Monday. It, um, so the reason for Monday is that next Tuesday we can discuss the homework. So the initial deadline I think was Tuesday. We changed it to Monday. So please make sure that you finish it before Monday. Practice test has been posted with solutions. You can go over them. It includes the problems for queuing systems. It also includes the question for network of queues. Any questions on the next test, which is on December 4th?
For going over the homework, are we going to go over it the 25th next Tuesday or the Tuesday after break?
25th next Tuesday.
Thank you.
So I'm not sure I'll announce, but Tuesday after break is likely gonna be off. But yeah, I'll announce that in the meantime. But next Tuesday there is a class. And since it is remote, I hope it does not interfere with the travels of most of you. Also, the test and the lectures in the last week following the test will be in person. There's no remote for the test. Any other questions?
We still only get a one-sided cheat sheet.
Yes. Yes, those instructions remain the same. So at least you see most of the formulas here are simpler. They don't involve matrices. So whichever formulas don't involve matrices, bring a normal calculator. You should be able to solve them to the last step, at least for this particular test. Wherever the system is bigger, that you can basically skip. Where there is a bigger than 3 by 3 matrices, but if it is up to 3 by 3, try to solve them to full. Like even in the class, we have been solving all the problems to the last step. We didn't need big matrix calculations.
Professor, I know it says in the syllabus that we dropped the lowest exam score of the midterms. Would it be
Yes.
possible for us to drop the lowest exam score or half of the final?
No, finals is compulsory.
Okay.
Any other questions, thoughts? So I'm assuming some of you have already attempted the homework. Does the homework seem reasonable? Yeah, we'll discuss the homework solutions. So there's a question in the chat, which is, are we gonna get homework solutions before test? So we will discuss the homework solutions in the next lecture. So if there are any questions remaining for the homework questions, please let us know in the next lecture. Tab 5 and practice 3, are they the only materials for the test? That's a question in the chat. Yes, those are the key things that we have given for this particular test. Right, assuming no further questions, we'll go over the last topic, which is reinforcement learning. Note that this topic will not be on any of the exams. This is basically just as a preview of basically how Markov processes can be used in other applications. But before we go there, there's one thing I would like to say for open networks. So one of the application of open networks, actually that's covered in the Kulkarni book, it basically says you go into an amusement park. You can go into a bunch of rides. So you go to first ride or second ride, and basically can keep on switching. It basically says examples as roller coaster, water tube, journey to moon, merry-go-round, fantasy, and other things. So you can do a single entrance and a single exit, but then after roller coaster, there's a probability you go to the different queues, and there's a probability after every one you can go to the exit. So that type of system is also an open queue type of system. So amusement park is definitely one of the example, and the entrance could be to any of the things. You can enter at roller coaster or at fantasy or at water tube or at merry-go-round. So you'll have different arrivals to different subsets of the amusement park, then probabilities to go across them, and then probability to exit from any one of them. Does that make sense as a practical example of open queuing systems? With that, we go over the last chapter of the course, which is Markov decision process.
Is this on the final exam?
It will not be because we'll only be covering it for 45 minutes. So we might not have enough for an exam. It's basically for understanding of how what we have done can also be used in other practical settings. So what we did in this course was Markov processes. What we are trying to understand now is Markov decision processes. So basically, what is the decision and what are we trying to learn? So let's go over them. So we'll go back to the finite states. So with discrete time Markov process, let us say. So in a Markov decision process, you have an agent that is making a decision, and you have an environment. So we already understood the concept of the state, which was the state based on which we were doing the Markov process. So process essentially means a time evolution, and Markov means basically memoryless. Those are the terms we learned. The new term here is the decision. So in this, the decision is basically you taking a decision. So think about you playing a game of chess. You are seeing how the chessboard currently is. You are deciding what move you make. And then you're basically exchanging the process such that your goal is maximized, which is to win. So this is basically Markov decision process started from Markov processes, as you can make a decision, um, make a choice of what move to make next, for example, on a chessboard. And reinforcement learning is basically an extension of Markov decision process where the system may be if the system is known, then we remain at the MDP type of framework. But reinforcement learning essentially models the MDP framework, with the only difference being that the system may not be known. So what happens is you observe a state at time t, which is st. Based on that, an agent, which is the player, for example, takes a decision, which is an action at. And then environment, based on the current state and the decision you make, the state changes, so it becomes the next state. And the environment also tells how good the decision is by giving a reward. And the state and the reward goes to the agent to make the decision. So there's a time wall here, so t plus 1 at the next time becomes t. So think of you learning to ride a bike. State is When you press, what happens, how much do you know right now. Action is whether you pedal in the forward direction, backward direction, what pressure do you put on it. Then the reward would be whether you go forward, go backward, fall, or whatever. And the next state is how much you have learned again after doing the current decision. So, this type of Markov decision process is useful in all walks of life around us. Very simple examples of the things around us. We could basically make a decision of a thermostat control where you can basically say, I want to save my energy bill. I also want to remain in a good temperature. Then, how much should when should I increase the temperature? When should I turn the air conditioning on or the heater on correspondingly? And how much time should I run it such that my overall energy bill is optimized as well as my comfort is optimized? So that is also some of the decisions that are made. Any form of robotics where you are trying to move the arms of the robot autonomously is actually a Markov decision process. You basically are like, I'm here, should I move a leg forward or a hand forward? What motion and what decision should I be doing? Where you are and what is the task you are doing, those gives you the state and the reward. Does the problem make sense? So the basic thing is you have a state in the start S0. You take an action A0, you get a reward R0, and then the system transitions to a state S1. You take an action A1, you get a reward R1, and so on. So there is a probability transition, which basically says given the current state and action, what is the probability of the next reward in the next state? This determines my system. So the difference compared to before, when we did the discrete time Markov chains, is we only had st plus 1 given st. Now the decision depends upon the action, and there is another signal which is the reward signal, which is basically used for decision making. Does that make sense? System or environment. Because the environment takes the inputs as state and action and gives you the next state and the reward. So if you are running a robot arm, you are basically saying, my robot arm is in this position. I move it with certain force in the forward direction. Then I get a certain reward and I move to a state which is the new arm state. Any questions on this? Right. So the next concept is the policy. Policy is basically what does the decision maker, the agent, decide. So the policy is a mapping from its probabilities of selecting different actions. Key is if I'm in a certain state, what action should I be choosing? So this is determined as what is the probability that I choose an action A at time t given that I see the state which is S at time. By assuming Markovian, we are also assuming stationary process, which essentially means all these t dependence is stationary, means whatever policy you are making at time t is the same policy at time t plus 1 and so on. Similarly, this transition is stationary. You can change any t, and this probability function will not be dependent on t. Any questions so far? So P is the system, pi is my agent, which is deciding the action. The question we ask in reinforcement learning or Markov decision processes is how do I determine this policy? So the question is determining policy. What is the action you take given that are in state S, and it could be a randomized process, randomized action. You take action A1 with certain probability and A2 with certain probability and so on. Does the problem seem interesting? That's good. So in order to determine the policy, the first question that we have to ask is what is our criteria of what policy is better, one policy being better than the other? So how do you determine goodness, or what is a metric to determine what is better? So what do you think could be a good metric? So one of the metric that is used is the discounted sum of rewards. It is defined as summation gamma to the k r. So this is basically r0 plus gamma times r plus gamma square times r plus and so on. So basically what is happening is you discount the reward that you get in the future. So if you are playing a chess game, for example, this will also make you win sooner. If you put a reward as 1 when you win and minus 1 when you lose, this objective will be basically winning faster. At first is winning and second is winning faster among two possible choices. So the intuition of this type of reward function actually came from diminishing returns, that if I give you something much delayed, we don't have as much gratification of it compared to we getting things now. So the future rewards are discounted in many types of setups, and that is basically what is here. In many practical examples, we still choose gamma very close to 1, but for most of the theory, we cannot choose gamma equal to 1, because what will happen is if gamma is 1, then the sum is infinite, because even if all the rewards are bounded between 0 and 1, it's an infinite sum. So in order to make the infinite sum as finite, we kind of use gamma. And if the reward is bounded, Then summation over gamma k is 1 over 1 minus gamma. So the sum is also bounded by the maximum reward upon 1 minus gamma. So that basically takes into account that this sum remains bounded and that we can compare one policy with another. Otherwise, we will be comparing two infinities and it won't make sense. Does this make sense? So the determination of a policy based on the state, of course, depend upon the rewards that you obtain. So our objective basically becomes the value function, which is denoted as value function based on a policy at a state S is expected value of summation gamma k, assuming policy pi, and the transition probability p. Transition probability is basically the system or the environment, which is the probability of next state and reward given the current state and action. So P is basically what the system gives, pi is something that we are designing. And that is why we have determined the value function as a function of the policy pi. And the optimization variable is this policy pi. And this S is basically given that this S, which is basically you start from the state S, which is, for example, in a chess game, we know the initial state where everything is at the front. Um, so, given the initial state, what is the best we can do? Does the setup and the method make sense? So, one of the interesting thing here is that if I'm given a policy, the transition probability st plus 1 given st is determined. Why? Because the environment gives us pst plus 1 given st and at. This is given by the system. You multiply this by probability at given st. So what do you get? The product is p of st plus 1 comma at given st. Then sum it over at. Sum it over at. You get p of st plus 1 given st. This was my first. So from the environment and your policy, I can get a state transition. So then the state evolution basically becomes a Markov process. There is no decision anymore. If you are given the policy pi, you can actually have the steady state probabilities of the different states. And then once you get the steady state probabilities of the different states, you can also get the rewards based on the steady state motions. So once the policy is determined, you can evaluate the policy, which is what is the goodness of the policy. So what we kind of do is typically we've basically given a policy, we can evaluate the policy. which means what is the value function for that policy, right? So that basically tells me that given any particular policy, for example, a randomized policy, I can see how good it is, and that helps me compare the different policies. So there is one of the algorithm which is called policy improvement. What it does is it basically evaluates a policy, then improves the policy, then again does the evaluation. So it basically keeps on improving the policies with the evaluation. But the main thing that I wanted to get across was once you are given a policy, determining how good the policy is essentially a Markov process. The decision comes in determining the best pie. And that is the basic extension between the Markov process and the Markov decision process. Any questions on this? With that, I hope I have given you a good preview of what a Markov decision process is. So let me give a brief on what is reinforcement. So the model is basically the probability of st plus 1 or t plus 1 given st and at. So there are different setups for this. The first setup is called as a known model, where you actually know this transition probability. Remember in our course, when we evaluated the Markov process, we assumed that we knew the transition probability. We had the data to know the transition probability. When we know the transition probability, that is typically called Markov decision process. That I know exactly the transition probability. And this is essentially also where most of the control system theory is there. So stochastic control. So stochastic control also typically deals with you knowing the system. Okay. Then there is a setup of unknown model that you do not know this transition probability, but once you get a give me a state and action, I can get you a sample of the next state and next step. So basically, the decision of next state may be stochastic, but you take the current action, and I will give you one sample of what the next state is, one sample out of the probability distribution. And this is how most processes actually go. You do not know the transition probability, but you take an action and then see what the next state is. That may not give you the entire, that does not give you the entire probability, it just gives us one sample. So unknown model is where we typically call it as a reinforcement learning. In reinforcement learning, then we divide it into two categories. One is model based and another is model free. Model based means I learn this p of st plus 1 rt given st and at from the data. So I take enough samples and learn it and then can use it. So basically, it is a problem of basically you learning the model and taking decisions with them. So you are allowed to learn the model. In model free, you do not learn, but still learn to make decisions. So the history of reinforcement learning, it has been a very old area. In 1998, reinforcement learning was able to beat the best chess players. So 1998, the models we used were the model-based reinforcement learning. And the reason we could use model based was it was a chess game. We could learn the opponent. Based on the opponent, we could basically. So, the key part of the system in a chess game would be learning the opponent strategies. If you learn the opponent strategies, then you learn the game. And of course, you need to know in the model base, you need to learn um, how much each of the thing, how much bishop can move, how much everything else can move, and what are the decisions possible and how they go into the system. And so learning the model actually involves both the components of learning how what are the things each move can do, as well, which is yeah, as well as learning the opponent strategy. Major part is opponent strategy. Um, the second, so chess game we already could do model based. For AlphaGo, we did not use model based. Even for actually chess games in 98 algorithm, I think we still use model free. So I can explain why model free compared to model based. So even if we look at chess game, there are 64 skills. So you had a tremendous state, which is you have to give me the state of every possible player. So there are 16 players that you have. Each of them could be in any of the 64 positions. So the number of states are 64 power 16. It means, of course, you can reduce it based on no two can be on the same position and bunch of other things. But roughly speaking, if each of your 16 players can be in any of the 64 positions, your total number of positions are 64 power 16, which is a lot to do for the state. So even if you can learn this system, it's very high dimension, and learning that many probabilities um, actually will need a lot of time, which we may not even. So model free, if I don't learn the system and directly learn the policy, then I can basically do it without learning the system. And these model free algorithms have been the key algorithms for reinforcement learning literature. So till 1998, we were at model based versus model free. In 2015, I think you might remember, reinforcement learning became popular because we beat the best AlphaGo players. And the difference we did essentially between 98 and 2015 algorithms, both of them still use model free algorithms. The difference we did was we parameterized the model free algorithm with a neural network. And given that neural networks became scalable, we could have a lower computation time for alpha. So these type of algorithms have been very popular. They're used now pretty much in every ML task. You might have already used them in GPT and other algorithms, where when they say thinking or basically evaluating, it's essentially reinforcement learning. So it's a critical part of every of the system that is coming on in the next years. Robotics, any of the agentic AI, everything essentially uses reinforcement learning. Fine tuning of the language models is also reinforcement learning with human feedback. So, my job here was to give you a preview of what reinforcement learning is and how it is related to the course that we did, and why the basics of this course will be important for even machine learning type of courses in the future, especially related to reinforcement learning, as well as any of the generative AI. Because even in generative AI, you are basically learning the distributions of the input. So I hope that convinces you of the different applications this course will have in the future, and the reason to learn this course for you and its formalisms. So with that, we basically end the syllabus of the course. Let me know any questions that we have. The next lecture will be a review of the homework and, if as needed, the practice test. Um, the last week of the course after the test will basically be discussion of the test and the review of the entire course for the finals. Any questions? If not, that's all for the lecture today. Thank you.
Thank you.
Thank you.
Thank you.
Recording stopped.